Hey, it's me, Destin. This is Smarter Every Day 2, the second channel where I like to take more in-depth looks on different things technically. In this case, this is a memory module for the Saturn V LVDC, launch vehicle digital computer. Now, I like to learn about rockets. It's kind of my thing. And Linus from Linus Tech Tips, he's a computer guy, right? So we are really interested in this stuff from different perspectives, but we're talking to a very interesting person, Luke Talley. He worked at IBM here in Huntsville during the 60s, during Apollo, also during the 70s, and he knows this thing inside and out. So this is a really fascinating thing because we kind of know what we're talking about in our respective areas, but it feels like Luke knows all of the things and he's just running circles around us. So this is fascinating. I hope you enjoy this, and let's take a deeper look at the LVDC memory module and just how all this stuff works. While you're watching this, please consider subscribing to this, the second channel, if at some point along the way you learned something that you think brought value to your life. If not, no big deal, but if you do, please consider hitting that bell to turn on notifications for the second channel. Anyway, let's go get smarter on the Saturn V launch vehicle digital computer. Look at this device right here. Don't touch this with your fingers.
Yeah.
But look how new this looks. But you see how it looks very similar to what we're doing right now. Similar.
Yeah.
We're taking a hard drive and we're plugging it in, and this plugs in, right? See that?
Yeah, here, I'm gonna pick one up as a prop.
So this is a logic controller, excuse me, a logic card. This is a logic card for the computer that flew the Saturn V rocket.
Really?
Yeah, and we're about to go meet the guy at IBM that worked on this.
Oh, I can't touch that part?
Nope, it's a special magnesium lithium alloy, so it'll corrupt. So you can touch
Never
it like
mind.
you can touch it like that. Yep.
Okay, that looked like a safe.
Yeah.
And that was just to save weight then?
Yes, exactly. Yeah, exactly.
Like literally every gram, or excuse me, every ounce.
Whatever you want it to
Mattered.
be, it doesn't matter. Yeah. So isn't that crazy? And so each one of these are like it's like some of the first transistor technology that was miniaturized. This is a big deal, man. Okay, so what we're gonna do is I'm gonna go to the U.S. Space and Rocket Center and I'm gonna show you this computer that flew the Saturn V rocket.
Because this is like your whole jam, right?
This is my jam. Do you wanna go see it?
Yeah.
Okay, let's do it. Is this interesting at all to you?
Oh yeah, no, this is incredible.
Yeah.
So you have some guys there that can like walk us through kind of the speeds and feeds and like how it all worked and all that?
Yes.
Cool.
He will tell you, this is not like an 8-bit system. It's weird.
Got it.
Yeah, it's very, very weird. So you see this ring over here?
Yeah.
So that's the computer.
That's the computer.
Well, the computer sits on that. And
Got it.
Yeah.
And there was a reason to mount it as a ring as opposed to just in some other configuration because...
You want to balance a rocket, right? You want the center of gravity to be right in the center of the rocket. So this is what I wanted to show you. So this is the brain for the Saturn V rocket. If you look up right here, this is the instrumentation ring. And so they had computers on here that were digital. This right here is the launch vehicle digital computer. That is it. That's like the original.
So this is so that module we were holding before.
Yes.
There's only like 8 of them,
Yeah.
at least in this chunk of it.
This right here is a memory module, okay? And if you look really, really, really close, you see those little bitty rings?
Yeah.
Okay, look right here. Look at that. Do you see that?
Holy smokes. So they're just, it looks like zip ties on chicken wire.
Okay, those are bits. Those are physical bits. So you see that screen?
Yeah.
These are wires that go down to these boards right here, right?
Yeah.
On each node, you have an iron ring. And depending on how the iron ring is magnetized, that's a 1 or a 0. That's how they programmed this computer. Seriously. So look at this right here.
So by hand.
By hand, yes.
They threaded these wires through the... I mean, who has a steady in it? Like, I don't even think you could build one of these today if you wanted to. That's incredible. So you get about 100 kilobytes, or kilobits. Wow, so like, what, like 15
It's right here
kilobytes
for you.
or something like that?
The whole thing, the whole module, 8 of those modules on the whole computer adds up to 112 kilobytes.
112 kilobytes.
But the magic of all this is that it was done by hand. And shoved on that ring right there.
And then sent to the moon.
And then
well, not all the way to the moon, I guess, but...
Yeah, you got it. Exactly. This got you to orbit, and then there was another thing that happened on the Apollo spacecraft itself that got you... Isn't that cool?
That's unreal.
So these are the memory modules, and on the other side of this, you can actually see the computer logic cards themselves. Do you want to go see that?
Oh, yeah, for sure.
Yeah, let me go show you that. So follow Pella. Who's this guy? Okay, so you remember I told you not to touch the stuff, right?
Yeah.
Okay, so this...
That's what happens if you touch it.
Yeah, so it's I think it's magnesium lithium alloy for weight, just like you said, and this just happens. Like, it deteriorates no matter what.
Right.
And it's a losing battle to try to fight it. But each one of these logic cards had those, you can see just down in there.
Yeah.
See them? And so it's like, it's not expandable memory. These are actually cards that you put in to do the processing.
Wow.
So anyway, this was cutting edge technology back in the day. Like, this was a quantum leap in computing power at the time. And it also had to be rugged enough to fly.
Yeah.
Anyway, I just wanted to show you that.
Oh, that's incredible.
Okay, and we have a guy here that can actually walk us through it and talk to us about it.
Sounds good.
Is that cool?
I'm Luke Talley, and at this time in 1969, I was a senior associate engineer at IBM in Huntsville.
That's awesome. And you were over the...
Working on the instrument unit.
On the
in the
computer.
flight evaluations team, we evaluated the data that came back and looked for everything that might go wrong or did go right.
And to be clear, this is for the Saturn V, not for the Apollo spacecraft.
That's correct.
So,
this is for the Saturn V instrument unit.
So your computer pointed the rocket.
That's right.
Awesome.
We steered the rocket.
Which one's you?
That's me.
That's you?
Yep.
When was this, Luke?
1969.
I think you look better now, man.
I was haggard after this.
Were you?
Yeah. This was the aluminized Kapton sheets that we used to cover the equipment and the cables. Because after we started looking at it, we found that several of the cables that were going into several of the boxes had failed as well. And then we did a sun angle calculation based on the output from the platform system.
Yeah.
And calculated where the sun should be. And then we went in and looked at temperature measurements in those areas, and sure enough, they were just climbing like gangbusters.
It liquefied.
So after that, the rest of the flights went
After
fine.
you put this on and just solved the problem?
Yeah.
So gimbal drift was a big deal.
Oh yeah. Gyro drift is always a problem.
That kills you, doesn't it?
Yes. Because this computer system senses that as true motion. It doesn't know any different. Gyro says I'm moving, I must be moving.
But you said the computer has a 2-second loop,
Right.
and it's comparing where it's at versus where it's supposed to be.
It's reading that platform 25 times a second. Every 40 milliseconds, it's taking a reading of where it is and where it's headed. And so
But how do you account for gyro drift if you can't like point at a star and recalibrate?
You zero it at launch, and then you know how much it's going to drift, and
you trust it?
you just trust it. Yep.
Holy cow.
That's what you got to do. You got to build a system that doesn't have that much drift. Now, if you have a long duration mission, then you have to worry about star tracking and this kind of stuff.
Because when you integrate, and you get the plus C
That's
at the
right.
end.
Now you start, the plus C at the end.
The plus C is the killer, isn't it?
Yeah, I hate those plus C's.
That's awesome.
It's stupid constant.
So you get it, man. That's
Oh,
awesome.
yeah. Been there, flunked that test many times.
Well, I'm glad you didn't flunk it when it counted, right?
Yes. I hated that stuff.
Really?
Oh, jeez.
And so then,
I had a retired Navy admiral teaching thermodynamics. This guy had memorized the steam tables to 5 places at least.
it was good.
I mean, what's the enthalpy and entropy and all that kind of stuff, and he'd rattle off the numbering. My God, he's got to be wrong. Look, son of a gun, how did he do that?
It's amazing. He just knew it.
Oh, yeah. So he'd been messing with submarines for 10 times longer than I'd been around at that time, I guess.
That's amazing.
Thermodynamics.
Check this out.
Yeah.
That's a pristine logic card.
Yeah, where'd you get this thing?
I got it from a guy in town. He's a collector. Can you tell me what that is? because I don't really understand it, to be honest with you. So to be clear here, this is Luke Talley. He worked on the the Saturn V launch control computer. Is that correct?
Mm-hmm.
Okay.
All right, this plugs into that board.
Okay. On the LVDC, the launch vehicles.
Yes. Well, it could be the one.
Okay.
It goes right there.
Okay. What does it do?
Well, these are the logic modules for the computer on the LVDC, on the Saturn. So there are, let's see, this one now has 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 25. So this is, if this is out of one of these, which it appears to be, this is probably out of an LVDA, okay? The LVDC has 35 modules on a board, okay? We call these MIBs, multi-interlayer connector boards, or whatever it was called.
Yeah, whatever.
Yeah.
Minor details,
All right.
I guess.
So we had 35 of these. There was 35 on this side, then there's 35 on the other side. The wing sticking out of each of these is these things poking out the side are your heat sinks. So you plug it into the rack. And we're actually pumping coolant through this rack to cool these things. This thing dissipated, the LVDC dissipated around 100 watts. The LVDA was probably closer to 200, 190 watts, something like that. This one was probably 85 or 90, somewhere in that range. So this was all what's called T²L. Each one of these modules now only contain, we didn't have any integrated circuits. So the spacecraft now, they did have some small scale integrated circuits built by Raytheon for them, for that computer. This one we did not. All right, so we have discrete transistors inside each of these modules. I just happen to have one. Okay, if you hold that, you can see up here there's two little squares.
Wow.
Each of those is one transistor. These two little shiny pieces up here in the corner, each of those is one transistor. They're about 25 thousandths of an inch square, a 32nd of an inch roughly, all right? So each one of these modules would have anywhere from 2 to 8 of these transistors. This one has more. Something that might be an inverter, draws more current, would have only a few. This would be in a flip-flop, a logic gate, and it would have multiple, probably up to 8.
And is that a thermal issue? How many?
Yes.
Okay.
The back of it, this thing here, these little black blobs are resistors. So if you look at the front, you see the two transistors and look like the wires that lead to them, the conductor pattern. And on the back, you see the resistors. There are also some conductor patterns. So they start out with this aluminum oxide, alumina, they call it, substrate. They print these patterns like you're printing a t-shirt. All right? Then you put it in an oven and fire it.
Yeah.
When you fire the thing, then that hardens it. You bring it out. Each of these transistors, if you can look real close, there are 3 tiny little balls of solder on the bottom of each one. You take it where the conductor pattern comes together, you stand it up on the 3 solder balls, put it back in another oven, heat it again, and the melting of those little solder balls will align that transistor perfectly. The surface tension of that melting will align that transistor perfectly with that conductor pattern. They tried all kind of neat ways to doing it, and that turned out to be about as neat as there is. Today, you hear about ball grid array attachments. That's the same technology. The resistors on the back, they would have to take an ultrasonic scribe and scrape those until it got to the exact number they needed to use.
Right, because that's not enough space to use your traditional little cylindrical resistor.
Oh, no.
No, of course not. You're
It doesn't
basically...
matter. It's 1,800 ohms, it's 1,800. We don't care if it's round or flat.
So you're basically taking the kind of the area in between these, and you're scratching away enough of the conductive material that you just create the resistance you need.
If you look very close, you can see where they've been scratched.
Yeah, it kind of looks like a cheese, like a Swiss cheese or something.
They call that trimmed. So basically, you hook it up to a Wheatstone bridge. Little scribe comes down, starts scraping until it gets down to, it's supposed to be 1,200 ohms. When it gets to be 1,200, it lifts off.
And then it stops.
It blows the stuff off of it, and then they coat it with some red goop to
just keep it from, I guess, corroding or
stuff from, yeah. I would think this more than likely is out of the numbers and all look like, the 6,000 numbers look like Saturn numbers. but most of the logic in here had pretty much almost a full board.
Really? So I brought you something thinking I would impress you, and you're like, take it away, boy.
Yeah. No, that's fine.
It's a pretty good one?
Yeah.
So we have something else
I'd
here.
like to have a few of those.
Would you? So, Linus, you want to show him this?
You go ahead. I think you're more familiar with how it works than me.
Well, I'm just going to hand it to you.
That's a memory module.
It's a whole memory module. So how valuable would you say that is?
I have no idea. You have to go to the Antique Roadshow. Now realize that this is core memory. So you have these magnetic cores, you have the wires feeding through the cores. You push a current down through a wire. All right, if you got a wire, if current's going in that direction, the magnetic field is going to be in this direction. If it's going this way, it'll be that way. Make that a 1, make that a 0. There's 8,192 of those on this plane, all right?
Yeah.
Then there's 14 of those planes stack up to make this module. This module is what you're holding. All this stuff now are the drivers to drive this thing.
That's just to program it as a 1 or a 0.
Because this is basically an analog process.
Right.
I'm not writing 1s and 0s into a logic gate and storing them that way.
No, you're just
I'm
sending a
actually
current.
having to magnetize a core one way or the other. And then I've got to read it. And when I read it, I destroy the magnetization. So I have to turn right back around and write it back in there so that it's not missing.
Oh, no.
So there's one of these in this. And then there's one of these now in each one of these blocks on this wall over here.
Got it.
So we have 4, 8, 12, 16,000 words of memory. Another 4, 8, 12, 16,000 words of memory. Now when the Saturn's flying, both of these memories are executing the same flight program.
Completely in parallel.
That's right. And they're comparing the outputs to make sure they're getting the same answer. If they were to not get the same answer, go into a subroutine and say, I'm at this point in the flight, I got these two numbers, what makes the most sense to keep using, use that number and keep going. So your critical parts are triple redundant in the logic, dual redundant in the memory. As I recall, during all the Saturn flights, we had like less than 10 miscompares, something like that. It was a very small number.
So did you pull the data down while it was flying?
Things happen too quick in flight too.
How do you know you had...
We get the data back and then we analyze. That was my job at IBM, is we were analyzing the flight data to determine what worked, what didn't work. If it didn't work on this flight, how do we fix it on the next flight?
Got it.
And then when you get the NASA requirements for the next flight, make sure we got everything in place to do what we are supposed to do. So the data tapes come from all around the world through Goddard Space Flight Center is responsible for that. So they get us the data and then we analyze it and determine what happened. A lot of the work was, by today's standards, was pretty crude. We would have something would go wrong in the computer, and it always goes wrong when something else is messing up the telemetry system. So we would actually get what they call an octal dump. We have this 11 by 17 sheet of paper, 10-bit octal numbers, so there were 4 characters, like 0 to 7, so as you go with octal arithmetic. So you got all these things, and I think it was like maybe 40 columns and 30 rows, something like that. So we would get this thing printed out, and all it's just numbers. Well, the piece we're looking for is at a particular place down here. Well, the dropout is where telemetry dropout. So we would actually get this printed out, 11 by 7 fan fold paper, spread it down the hallway, get down on your hands and knees, make a template, cut out you'll have a number of measurements that'll always be the same,
right.
Like a voltage that never changes.
Yeah.
So we know what those numbers ought to be. So we cut the holes out and slide it down page by page. Oh, hey, these all look good. Okay, this frame's probably good. So we go find so many columns, so many rows, find the number we want, write it down.
So you're looking for one that if it bungs up something that you know is a fixed value, then it probably bunged up something else.
That's right. And if the fixed value is okay, then somewhere in there, our number is probably okay.
And then once you've got the problematic one, I mean, is that just the world's nastiest Sudoku puzzle, or how do you solve that?
You may have to do this for many, many, many frames. Then you take it to your desk and take those octal numbers, convert them to decimal numbers, go to a calibration chart and say, okay, I got this number.
Yeah.
Go up my chart and say that means it's 5 degrees centigrade. So you write down 5 degrees and you figure out what frame you are. That's about what time it is. So at this time I had 5 degrees. Then you go to the next one. Now you do this for about 2 weeks and finally you got enough to plot a graph by hand. So you put all these numbers in and you plot it by hand, and then you say, that wasn't a problem after all. Oh well, here we go again. So,
Oh boy.
This is Ed.
Hi.
Ed is the head
Hey
curator.
Linus, how are you? This is kind of an in-the-hand example of the memory cores that you can see woven into the spread here and then kind of under the magnification over here. And there's about 8 or 9 of them in there. So like Luke was saying, when you run the current through there, it starts to spin that donut in a particular direction, and that tells you whether it's the 1 or the 0. And you're saying they were woven on by hand. It was primarily women that did the work, that had basically a bench top.
So they would have like textile industry experience, I guess. Or
I actually am not certain what their qualifications were, but they would sit with a bench top with this thing mounted in a holder
yeah.
with copper wire lengths and tweezers and their fingers and a lot more patience than I have to weed these things through there to make sure that they went through appropriately, no kinks, no bends that were out of a spec, and to actually make sure that the little donuts go into across, you know, the way they should, and that was all
Right.
uniform, so everything would be predictable behavior.
Incredible.
So,
I just wanted you to hold a physical bit. Now you know what that's like.
Yeah.
yeah.
I mean, this is more than 8 bits, so this is I'm holding at least a byte. Think about it that way.
So when you look at this, what kind of emotion do you feel when you look at this, Luke? Are you
Is it
proud?
fondness, or is it more just thank goodness I don't have to work on that bloody thing anymore?
no, I'm going to talk to one of my buddies when you go out the building here, see if he hits you in the head.
to get this thing?
Yeah. No, that's a real piece of work, you know, and it looks, to people that come in here, they say this just looks so much like an antique. But again, we only had a few failures during the whole flight that were intermittent. We
People-
never had a catastrophic failure.
People might say antique, but I would say handcrafted.
Yes, there's a lot of handwork went into these.
Oh, you can tell. I mean,
doubt.
even they're clearly hand bent.
Well, they've got the goop on them, because the big problem with this thing is vibration. Though
Right.
the memory that we were looking at over there,
Yeah, you've got physical
they
rings
test
on
and-
there.
They test and test and test on that thing to make sure that you hadn't got a kink in a wire or a twist, because if you do, the vibration is going to cause it to break. Those things were made by hand. The ladies actually wove these things like you're weaving a piece of cloth. Pretty amazing. Now, 16,000 words of memory,
Yeah.
26-bit words,
Okay.
and we had
Okay, that's-
2 extra bits, and that was for parity, for error checking.
Got it.
So actually 28-bit words. Today, everything's 32 bits.
Right.
Now remember, every time you add a bit, you double the amount of stuff. With this thing, you look at this, and you look at the core plane, and you look at the work that goes into it. So you don't want to add anything more than you have to. So with this thing, they realized that 26 bits is the biggest data word I'm going to ever have to make this mission fly. I can take those and split them up into 13-bit syllables, and I can use those for data words, and that will cover everything I need. So you stop at what you need, 28 bits. You don't go on to 32, because 32 will be 2 times 2 times 2 times 2. That many more times, 16 times more expensive than this was. And
Got it.
unreliability. That's the key, because the more of these things, more cores you add, the more of this stuff you need, the more unreliability you add to your system, because sheer numbers of parts.
Right. And when you're
trying-
talking physically assembled
Right.
parts.
Right. You're trying your best to keep the reliability numbers up as high as you can on this thing. So the less parts you have, the more reliable, provided they'll do the job.
Got it.
Which worked great. Now, this computer, the digital computer, is an outgrowth of what was done on the Titan missile. Okay.
Oh.
This is an outgrowth of a follow-on from what was called the ASC-15, which was a Titan missile computer, which IBM had done for them. The Titan used a combination digital and analog. We did the same thing here. Okay? This computer controls all the timing, start engine, stop engine, fire separation rockets, fire retro rockets, all this kind of stuff. It does navigation and guidance. You have stored in the memory a profile. At this point in time, I need to be here, going this fast, going in this direction. You have stored where you want to be.
Yeah.
This thing now is reading the guidance platform information 25 times a second, and he's calculating where am I, how fast am I going, what direction am I going, all right? Computer now, he's operating in a big 2-second major loop, they call it. And then within that major loop, he's getting interrupts to do other things. We didn't have an operating system. Just got this big major loop that we're executing over and over and over and over. Navigation, guidance, control, interrupt. Go do something. Come back. Navigation, guidance, control, interrupt.
Now,
Go
what
do
would it get
something else.
interrupted to do?
It gets interrupted.
Someone flips a switch?
Gets interrupted to read the platform, the guidance system, and say, all right, I need to 25 times a second, I'm going to get an interrupt that says, go read that platform information and calculate where am I, how fast I'm going, and so forth, all right? It gets a timed interrupt that says, it's time to issue a command down to open a valve in the first stage, all right? All stored in memory. He's set a little timer. He's setting over here saying, okay, I got a next switch selector must be done at this many seconds from launch. He sets a timer, counts down to 0, says, 0, I go do this.
So there's no advanced scheduler on the CPU itself.
Well, but
it's manual, like a manual scheduler.
That's what these switch selector commands are that are stored in memory. They're the scheduler. When that thing interrupts and says, go do this switch selector, you go do it, okay? And you come back. Then they have things like when the stage separates, engine shut down, those are all interrupts. We'll start time-based differences and so forth. So all of that stuff is going on continually. Now, the navigation, it's got the stored profile. That's where should I be. He's read the platform information, done the computation.
Yeah.
Here's where I am. I'm comparing where I am versus where should I be. That's navigation. Churn. What's the error? Hands it over to the guidance routine. The guidance routine says what's the best way to get from where I am to where I should be in the next 2 seconds, my major loop. So he churns with the guidance, comes out of the guidance thing, says, hey, I got to make this correction. Now it's time to wiggle some engines to get me to where I'm supposed to be. He hands that command over to this thing that looks like a barrel. That's an analog computer, okay?
Analog computer.
Now this thing takes a set of rate gyroscope inputs that are another set of gyroscopes besides the platform guidance system, and it's measuring how this vehicle is moving physically, all right? Each axis. So they're feeding into this. Now, this thing takes this command from the digital computer, says, I need to make this amount of correction. He looks at the rate gyro and says, well, this guy wants me to make this kind of correction, but I'm already moving in that direction. So I don't have to make that much. Or I'm going in the wrong direction, I got to make a whole lot.
Now,
and then he in turn sends a command down to move an engine.
Now, when we create a gyroscope in a modern phone, for example, we basically just print. We just print onto a circuit board. Like it's tiny. Now this.
That's a piezoelectric transducer. These are spinning mass wheels. These gyroscopes are spinning mass, just like your toy gyroscope you had as a kid.
And so we're
just
actually.
They cost $1 million a piece instead of $1.95.
And so because it's an analog computer taking actually moving spinning components.
No. This computer's been reading the gyroscope.
That one's reading the gyroscope.
The main platform system. This one's reading another set of gyroscopes.
Okay.
But the gyroscope now just outputs, hey, I'm moving this much in this axis, X, Y, or Z.
Got it. And then how do we read that? Is it a voltage output or?
These were voltages. The ones at this reading were pulses.
Got it.
He actually gets a pulse. Every time he gets 0.05 G's of acceleration, he gets a pulse. Okay?
Got it.
So the computer now is summing these pulses to determine what his current velocity is. The integrating acceleration gives him velocity.
So at that time, tell me, what was more accurate? This one or the digital system? What was more granular?
Those are a lot more accurate than this, yeah.
Got it.
The problem with this is when you're trying to calculate a long-term flight, all right, the problem is drift. Gyroscopes have friction. Friction causes the gyro to move. Any motion in the gyro is picked up as physical motion. To fly this thing, you have to have a much more accurate gyroscope in the guidance system than you did in the rate system. The rate, not quite as accurate.
Got it.
Did you account for gyroscopic precession as well?
Yeah.
How'd you do that?
That's all.
How did you know to
taken-
do that before the flight?
That's all accounted for in the processing.
And programmed into
you
that.
test and test and test and test. That's how you do it. You test these poor machines until they're just about worn out.
And then you take them to the moon.
Right. So, the flight control computer, the analog computer, actually sends the command down to move the engine. Now, remember we said we're in a major loop, 2 seconds. So he's going to send the command down to move an engine. And it's going to be 2 seconds before he gets another command to wiggle that engine anymore. So he's going to move a little bit, and a little while later he's going to move a little bit. Take, for example, the first stage. Those engines are so big and powerful that when you move it, you move the rocket, but you also induce flexure modes, bending modes. The poor astronauts sitting up there in the spacecraft, 300 and some odd feet away, they're really feeling this. We asked one of them, said, what did it feel like when this thing is flying? He says, it feels like you're riding a train on a bad track. And that's because you're getting these
Every 2 seconds,
Change, yeah.
it's moving around.
Right.
You're about to see Linus get very interested in the thermal system of this computer. If you've seen his channel, you know he's tried to liquid cool everything. So the questions he's about to ask Luke are from a modern computing perspective, but he's trying to put it in historical context. And Luke is providing that historical context. So this is a fascinating exchange for me. I enjoy this.
All right, the computer, basically, the instrument is divided up into 3 pieces. You start about here, and you're going up to the flight control computer there, and that's pretty much your
the round
navigation.
one, right?
Mhm. That's pretty much
Okay.
your navigation guidance control section.
So about a third of the ring or so.
Yep.
or third to a
Then the
quarter.
top part up there, that's mostly your telemetry packages. And then down over here we have the umbilical plate, then we have the environmental control system, then we have the 3 big batteries there, the water supply for the cooling system, and then these are auxiliary and main power distributors for the system. So this is sort of your environmental power system. And that's kind of the way it's divided up. The plates, sort of goldish looking plates.
Yeah, are those, what are they,
Each one of
brass or-
those, we're pumping, they're aluminum. You're pumping coolant, it's anodized aluminum. You're pumping coolant through there to cool the components. Each component, each plate would dissipate about 420 watts.
Oh, interesting.
So that's how you're cooling the equipment. Some of the equipment, like this platform here and the computer, actually we
You're
feed
actually
the
plumbed
coolant
into it directly.
and there's passageways inside the unit. We have the same thing in the digital computer and in the analog computer.
Got it. Now, what I don't actually see is where you dissipate the heat to, because
That little box up there that's got a little gray box that has the 2 plates with writing on it,
yeah,
it's called a sublimator.
a sublimator.
And that's how you dissipate the heat.
Okay, so that's
Essentially, a sublimator is a box, just conceptually how it works. It's a little more complicated, but fundamentally, say you have a box, you have a tube coming in that has the coolant in it. Just say a coil of tubing going through that box out the other side.
Yeah.
All right. The plate now that has the writing on it, remove those plates before launch. Say they've got tiny holes in them, pores, very microscopic. Once you get out of the atmosphere, then you open the valve, and this other thing that looks like a barrel is full of water, and then has a bladder in there. So it fills the sublimator with water. Each of those little pores forms a plug of ice. That ice now sublimes, goes from solid ice to vapor. And that's cooling it. That's how you cool the astronauts. When they do an EVA, they have a small sublimator on the back of their backpack, and they have underwear that has tubing, and they're pumping coolant through that tubing. That will dissipate 9,000 watts. That's a pretty amazing little gadget.
So forgive my stupid question, but a typical air conditioner works on a phase change cooling concept, where you go from liquid to gas and gas to liquid and use a compressor.
Right. We
So-
don't have to have a compressor with this.
You have no compressor.
We've got a couple of pumps in that, right above that single battery by itself.
Yeah.
Those 2, they're coolant pumps. You just have to circulate the coolant, but you're not pressurized. It's not a refrigeration cycle.
Huh.
It's magic.
It is not magic.
That's pretty good. That's a pretty good cut point for that.
Thermodynamics, first and second law, just put into action.
Okay, so what freezes the water in the micro pores?
Well, you're exposed to space out here,
Yeah.
and you got pressure down here, and it's a porous. You know what sintered metal is?
Actually, yes.
Okay.
Okay.
This is sintered metal, so you have
Yeah.
tiny passageways through there.
And it's making its
And
way
it actually
very
makes its way
slowly.
through, and here I'm exposed to space, and I've got water pressure down here. I form a plug of ice, and that little plug of ice goes directly from ice to vapor, just like you're sweating
Because
going
there's no
from
pressure.
liquid to vapor. Right.
And that's because we have the benefit
Because
of the
we're in
low
a
pressure.
vacuum of space.
So does that work during the first part of the launch? Not at all.
And what I said, you got to wait to get out of the atmosphere.
Out completely or at the edges?
Pretty much out.
Pretty much out.
About 180 seconds. That's the third stage is about just started to burn, I think.
But you've got enough water in your reservoir that you can absorb the heat while you're making your way through.
Yeah.
Pretty much.
It only went through a couple of cycles during the boost phase. Once you get out into, once the crew separates,
Yeah.
that's the biggest problem, because we start getting sunlight in here and things get hot pretty quick, and it really starts cycling on and off pretty fast. Basically, the coolant temperature is cycled between 50 degrees and 60 degrees. You get above 60 degrees, the computer
Bring it
sends a
down.
command, says, open the valve, fill it with water, and then
Let it
it
work its
drives
way
it on
through
back
and
down. It gets down to 50, closes the valve, and it'll start heating back up, and it just slowly cycles back.
Now you can only carry a very small amount of water.
All we got lasts 11, 12 hours. That's when the batteries run down. So that's plenty of water in there.
Golly, you remember all this. It's unbelievable.
Well, according to him, it's simple.
I'm just making it up.
No, seriously,
No,
like I've worked
yeah,
on
this is-
I've worked on systems like a couple years ago, and I don't remember them to the level of detail that you remember
Yeah.
this.
Yeah, this was quite a system, really.
Okay, so can you tell me about the spherical one? Is that this?
Okay, that's this.
Yeah. Is there,
That's
is
your
there
platform.
Two? Is that redundant, or what are we looking at
The
here?
platform, all right, you asked about the gyroscopes?
Yeah, yeah.
The gyroscopes are spinning mass, just
Are
like
those spinning?
no.
Oh.
I'll show you there in a minute.
Okay.
You basically have a spinning wheel,
Yeah.
motor driven.
Okay.
Instead of having ball bearings, our bearing is gaseous nitrogen. It's floating in
So
a
there's no
film of
contact.
nitrogen. Trying to get that friction down to get those drift rates as low as possible.
Can I ask another dumb question? If you want as little drift as possible, why nitrogen? Why not helium? Why not a vacuum?
Nitrogen's a lot cheaper.
So there were still cost constraints.
Yeah. Well, what we've got here is a system. Remember, we said the computer came out of the Titan. Well, these came out of the Jupiter programs.
Okay.
Okay. Pershing, Saturn, and so there was no real need to go to anything that drastic for the short duration mission we have. Now,
Got
if
it.
you had an extremely long mission, that's a different story.
Got
On
it.
Skylab, we were 9-month mission. So we actually use rate gyroscopes and use navigation updates using sun sensors and star trackers and that kind of stuff to periodically zero us back to where we were. Long duration, you got to take a lot more steps than you do here. This is a short duration mission.
Got it.
We only had to be accurate for 6 minutes, 9 minutes, 11 minutes to get to orbit, another 6 minutes to get from orbit into the translunar trajectory. Those are the important times, so very short time really.
Got it.
So the nitrogen is supplied by the sphere.
Oh,
The
so that-
electronics is in these 3 boxes here.
So this is just
This is
a
nitrogen.
just compressed gas ball.
Right,
And then this
3,000 PSI, and these are just
is
regulators.
Okay.
If you did this today, you wouldn't use that. This would probably be a ring laser gyro. Electronics, you wouldn't need that. Probably all fit in this box.
Right.
You go to a 747, that's probably about the size box they'd be using.
Got it. Now, can you, I mean, this might not be your specialty, but can you tell me anything about the cabling here? Is this fiber optic? Is it copper?
That's known as wires. Just plain old wires. When we did this, fiber optics hadn't even been thought of yet.
Got it. Okay.
Okay, so just plain wiring. Most of the, as I recall, I think the insulation is probably Teflon. These now are coaxial cables here. We had some other coaxial cables that ran around this that were more along like what you might see for cable TV on the pole. Actually had aluminum outer tube, polyethylene dielectric, and then the center conductor was copper. And that would be going from this CCS transponder up to the antennas for the long runs.
Oh,
These
okay.
shorter runs, they just use RG coax.
Okay, so sorry, this is going up to an antenna for what? Is that for communication or?
Yeah, this system has several pieces of telemetry. The ones up top up there, VHF, we had UHF telemetry on the early versions. These were VHF, and then this was S-band, 2200 megahertz, 2282 I believe it was. This is the transponder, this is the power amplifier, this is the coaxial switch. We had a high gain antenna, a low gain antenna, and two omnidirectional antennas. For the high gain, low gain, you got to point position one toward the ground so that you can pick it up. The Omni, you don't care where, you can pick them up, but the signal's a lot weaker.
Right.
Okay. So this thing now would telemeter primarily the computer telemetry we're talking about with the big sheets of paper and the octal dumps.
Yeah.
So this transponder would primarily do that, but it also had the command system. So you can send a command up when you get into orbit. During boost, you can't do anything. Things are happening too fast.
It's just going.
So once you get into orbit, Houston can say, well, we need to recirculate something in the S4B stage. So they can send a command to the LVDC through this, okay? Through this, sends it to the LVDC, and then it'll execute whatever they tell it to do. You can update you can do nav update, you can do a lot of different things through the command system. So this is both deals. The other thing is on the later missions from 13 to 17, we actually would crash the third stage in the instrument unit. They stay stuck together. They don't, once they're mated at the Cape, they're mated for life. They never separate. So we crashed those into the moon. Yeah. And we used this transponder. We added an extra battery so that we could track this transponder all the way to the moon. And when it quit, then we knew we'd hit the moon, and they could take that and correlate with their seismometer data. S4B, an instrument unit, hitting the moon is about equivalent of 11 tons of TNT. It would produce about a 2.5-hour moonquake.
Oh, wow.
So you would use, when this RF died, that's T0 for impact, and then you would compare that to the RF for the seismometer on the moon.
Yep.
And that's how you know it was a 2.5-hour moonquake.
Well, the seismometer just kept on for 2.5 hours, yeah. Wow. Before that, seismometer is pretty quiet. You don't hear much. You get small quakes. You always have a little bit of rumble on the moon. I can see the little green men running around, oh my God, the Americans are back. You don't have to put that in.
Yeah.
The reason for that, one of the science objectives on Apollo was to determine if the moon had a molten core. By doing this experiment, they hope to take that telemeter data, the seismometers, and determine. Originally, the data was very noisy, very difficult to determine. About 6 or 7, 8 years ago, I don't remember exactly how long, a group out here at Marshall, Dr. Renee Weber, Planetary Sciences group, they took that old data, cleaned it up with modern signal processing techniques, and determined, sure enough, the moon does have a liquid core. You can go out on the internet, and she has a diagram that shows this concentrated iron mass in the center, just like the Earth, has another layer of molten around that, and it has a layer that's not quite solid yet.
Huh.
And the moon is slowly cooling over time.
Oh, this is fascinating. Thank you very much, by the way.
Hey, thanks for watching a 30-minute video on the second channel here. You clearly kind of get how my brain works. This is a more in-depth look at how this stuff works, and you clearly are a pretty smart person that likes this stuff. So I think you might also find this interesting. This was on loan to me from a guy named Mark. He has a website called rocketrelics.org. I think you'll like that. I mean, if you're watching a 30-minute video, you're into this stuff. Big thanks to Mark for letting me borrow that stuff. Thanks to you for watching this. If you feel like this added value to your life, consider subscribing and maybe even ringing that bell to be notified when something comes out here on the second channel. Thanks to everybody that supports Smarter Every Day on Patreon. Thanks to Linus for doing this with me. He's got a video you can go check out. Yeah, I guess that's it. Thanks for sticking around. You're pretty awesome. I'll give you a fist bump on the way out. I'm Destin. You're getting smarter every day. Have a good one.